Welcome to machine learning. This is CS6350 if you're a grad student, and DS4350 if you're a data science undergraduate student. If you are in neither one of these groups, when I'm looking away, feel free to leave the room or hang around. I don't care. So the plan for today's lecture is actually it's the plan for the entire semester is to try to answer this question here. We're going to try to understand what is machine learning. In fact, it's not just machine learning, right? It's all kinds of learning. All of us are here to learn. All of us have been learning. And so clearly we know something about it. So let's try to think about what learning is. So that's the goal for today's lecture. We're going to answer what is learning, especially of the machine kind. And to get things started, rather than actually trying to focus on anything technical, let's play a game. So this is a recreation of something that happened in 1994. Every year, there's a conference called the International Conference on Machine Learning, ICML. It's one of the top machine learning conferences in the world. And the 1994 version of this, something peculiar happened. Every attendee, if you've been to a conference, you know every time, the minute you register, you get a name tag with your name and other information. Every attendee's name tag had a mysterious plus or a minus labeled assigned to their name. And only one person supposedly knew how these pluses and minuses were created. That was Chaim Hirsch. And the information that was given to the attendee was this choice of whether your name got a plus or a minus depended on nothing but your name. So it's not, it doesn't depend on, I don't know, the color of jacket that you're wearing. And the task for the attendee was, as you're attending the conference, talk to people and try to figure out what that rule was that he used to generate a plus or a minus. This is primarily an icebreaker event. You know, in more mathematical parts of computer science, people tend to not want to talk to each other. So this is a way to figure out, get people to mix with each other. And also the idea was that it's almost a challenge. This group here that in 94 represented perhaps the best in the world in the field of machine learning. And the challenge was, you claim that you can discover hidden rules from data. Let's see if you can. So that's the game we are going to play. Here are the kinds of rules that you might have seen. If the second letter of the first name is a vowel, then the label is a plus, otherwise it's a minus. It turns out that was actually the rule that was used in the conference. Or it could be the first name is longer than the last name, it's a plus, otherwise it's a minus. And things like that. So last night I decided to label the data using a rule of my own. And let's say you're walking around the conference and you run into Claire Cardi, and you see that her name has a minus. And then you meet Jude Shavlik and you see that his name has a plus. Can someone guess what the rule was that I used? Yes.
If the first and last names have the same letters, it's a minus, otherwise it's plus.
If the first and last names start with the same letter, it's a minus, otherwise it's a plus. It works for Claire Cardi, works for Jude Shavlik. Any other rules? Yeah.
If the first and last name have the same amount of letters, it's a minus, otherwise it's a plus.
Is that right? 6 and 6. So just to repeat that, if the first and the last letter have the same number of letters, it's a minus, otherwise it's a plus. So in both cases, it turns out, just coincidentally, in both cases, according to both rules, Chaim Hirsch should be a minus. Right? And I saw a few other hands up. So presumably, there are other rules that you can think of. But how do you know you're right? Maybe if you look at Chaim Hirsch's label, you'll know whether there's some evidence or not. Well, it turns out it seems to work. Let's say you see more data. Any other ideas? Let me tell you, since I was the one who created the rule, neither of those are right. Usually around this time, when I introduce the other data, one of the examples proves the rule wrong. But in this case, I think maybe not. But yeah,
The first letter of the first name is between A and H. It's a minus. For all other letters, it's a plus.
oh, that's clever. It seems to work. It seems to work. Any other ideas? But here's the cool thing, before you even think of ideas, notice that once you come up with the rule, once you come up with this hidden function that I had, you really don't care about the data anymore. You can assign labels to anything. You can assign labels to any two words like Indiana Jones, or my name, or your name. So once you have discovered this rule, it doesn't matter what the data says, you can go apply it. The tricky thing is, how do you know that you got the right rule? How do you know that you got it right? So let me also reveal the answer. Not reveal, I'll tell you that the third rule that was suggested was also not the one that I had in mind. So if you're interested, there's a full data set on the class website. You can take a look at it and try to guess what the rules were. Don't do it now. You can take a day or two and you can tell me on Thursday. But at the heart of it, this is what machine learning is trying to do. There is some hidden function that someone creates. Usually that someone is nature. And our goal is to use computational means to discover that rule. So what's machine learning? Before answering the question, I'm hoping that you're all convinced that machine learning is everywhere. And all of you are already using it. If you've used any, if you bought anything online and you get recommendations of more things to buy, there are machine learning systems that are processing your data to kind of make suggestions. If you've ever used any translation engine like Google Translate, it's a shining example of a machine learning success. The self-driving cars rely on many different machine learning systems interplaying with each other. If you use any sort of phone assistant device, I'm not going to name them because then they'll start asking questions. Once I made a mistake of naming such a device, and a whole bunch of students' devices responded back to me. But you know what I'm talking about. And you know this other thing that I'm talking about, which we'll talk about that in a bit. ChatGPT, large language models, all of these are products of machine learning. In this class, you will build none of these things. Because these are not just products of machine learning, but fantastic pieces of engineering, like unbelievably amazing pieces of engineering. But you will learn the principles of how such things could come into existence. Perhaps the oldest instance of machine learning as a product was actually spam detection. It's been almost 20 to 25 years now, where spam detection is done using machine learning systems. If you take photographs of people and you get those little boxes around people that say this person is Uncle Bob, there is some sort of underlying machine learning system underneath. Movie recommendations and purchase recommendations, stock price prediction. Hedge funds use a lot of machine learning to make a lot of money or lose a lot of money. Another early success for machine learning, a very early success actually, now going back to almost 30 plus years now, was handwriting recognition. I found out recently that USPS uses some rather interesting pieces of machine learning tools to sort mail, and it gets it right billions of times a year. If you think that your mail got lost, those are like tiny fraction of the times that it actually did not get lost. So it's a very successful application. Entire industries are driven by machine learning products because they help decide what ads to show you and where to place them and how to craft them. If you want to read text in a language that you do not know, like I said, Google Translate shows up. But also there are other really cool applications that go beyond making money. There are machine learning based systems that are in play to discover genetic markers associated with conditions like Alzheimer's and Parkinson's and so on. One of the big successes of one of the big achievements of science in the 21st century is this idea of protein folding, AlphaFold. I think it's a Nobel Prize winner as of 2024. Another cool idea, imagine that you want to design a new material that can survive re-entry from space and can only be built using things that are, whatever is available locally in Utah. There are research projects underway, even here at the U, that take these sorts of descriptions of properties that you desire, and then it converts it into 3D crystals automatically. We will not be talking about many of these things, but at the end of the semester, you'll kind of have a sense of how the very basics of these ideas, these kinds of things work. Notice I kept asking, what is machine learning? I promised to tell you what's machine learning, but I kept switching topics. So let's actually try to define machine learning. So that's the goal for today. We're going to try to define machine learning. Perhaps the first research paper with the phrase machine learning in it was from 1959. This really fantastic paper by Arthur Samuel that talked about building a program that learns how to play checkers. Just to put this in context, 1959 was so old that it was before transistors became a thing. It was, computers didn't look anything like what they do now. The notion of programming was very different. Your favorite language did not exist at that point. I don't know what your favorite language is, but I know it did not exist unless you wrote your favorite language is COBOL. If it is, then I don't know what to say. So in this paper, Samuel wrote that expressed this vision of how we should program computers to learn from experience rather than actually writing code. So rather than writing code to do things, you write code so that the program learns to do things. And that way it can acquire capabilities that it did not have before. And at the end of the paper, he says, he shows how he could do this with some early versions of machine learning at that point. And then he says, based on this, I think that machine learning might be economically feasible at some point in the future. Talk about, having a vision. While there's no clear definition of machine learning here, there's a hint of it. Programming computers to learn from experience. That's really the heart of it. Let's go to another person, Herbert Simon. Herbert Simon was a polymath. Until last year, he was the only person on Earth to win both a Nobel Prize and a Turing Award. As of now, there's another person, Jeff Hinton. So it turns out that both of them are people who do artificial intelligence. So in 1983, in this work, Herbert Simon said, learning denotes changes in systems that are adaptive, in the sense that they enable a system to do a task better the next time it encounters it. Imagine your program. Imagine writing a program to do something, I don't know, to sort a list of numbers. And imagine that your program mysteriously gets better at sorting the next time you run it. That'd be amazing. That's the dream here. And in some sense, he also kind of expressed this idea that this is a vision that's important and it needs to be a core part of computer science. I love this quote from the paper. Old programs do not learn, they just fade away because you need programs to adapt. Maybe the closest to a well-formed definition of machine learning is from this textbook by Tom Mitchell called Machine Learning. Tom Mitchell is faculty at CMU. He writes, a computer program is said to learn from some experience E. So the program keeps acquiring experience. And it does not, so let me just read the definition and then I will kind of tease it apart. A program is said to learn from some experience E with respect to a collection of tasks T and a performance measure P if the performance in the tasks as measured according to P improves as experience increases. So the important points are, first of all, your program gets to experience things. Your program gets to encounter more data, for example, or it gets to interact with the world. And there is a certain process that ingests this experience. The second thing is there is a class of tasks we care about. You do not want your program to be able to detect an email as spam and also learn to play chess and also fly a drone and do other things. You have a collection of tasks that you care about, and you want your program to do well at those tasks. So that's the relevant kind of experience that you'll be giving the program. And for each task, there is a well-defined measure of performance, some definition of success. And you need to commit to that definition of success even before you actually start this agenda. And Mitchell says that the program is set to learn if, as the experience increases, this performance of those tasks gets better. It does not talk about how. It does not talk about neural networks. It does not talk about random forests. It does not talk about any algorithms. It doesn't matter what's happening inside the program. As long as the performance increases with experience, your program is set to learn. This is the closest we have to a well-formed definition for machine learning. By the way, feel free to jump in, feel free to ask questions. I like the class to be interactive. Also, people on Zoom. Any questions? One of the most important things to note from this definition that Mitchell has, and the previous one from Herbert Simon, is the idea that you want your program to do well, not on the experience or the data that you've already seen, but on what is to come next. The most important lesson for today is that learning is all about generalization. It's about doing well on unseen inputs. It's about getting the right answer on things that you've not seen. Imagine that you take a class and you get an exam question, and your entire exam question is nothing but a copy of your homeworks. Sure, I mean, that tests how well you can memorize the homeworks, but that doesn't tell me anything about whether you understand the material in the class. The best way to judge whether this program actually knows a certain skill is to test it on new situations. So learning is generalization to new inputs. That's the most important part about learning here. Learning is generalization. For example, a popular application for machine learning is to detect objects in pictures. Imagine that you have a program that looks at these colorful things in these pictures. Can someone tell me what these are? Dogs. Excellent. That's not a trick question at all. Imagine that your program looks at these 9 pictures of dogs and learns the concept of a dog. To understand whether it actually learns the concept of a dog, it's not sufficient to know that it gets the right answer when these 9 pictures are given to it again. It has to generalize to new kinds of pictures, new dogs that I don't know what that is, that thing there. So learning, by the way, I'm sure that all of you hopefully recognize that thing at the end as a dog, right? Isn't that amazing? Have you seen that dog before? Isn't that amazing? Like, you've generalized. You have a unbelievably amazing dog detector. I don't know how you trained. Machine learning, I used to say, is the future. But the future is here. It's this incredibly cool way to think about programming, where we give programs the ability to perform tasks in situations that they have never encountered before. Programs that can acquire new capabilities. Those of you who've taken programming classes before, and hopefully all of you are excellent programmers, you know that usually when you write some programs, they just stay. They don't morph themselves into getting better as time progresses. If anything, somehow they manage to get worse. So this is a new way to think about programming. And it's an important sort of a conceptual tool to have in your toolkit because it allows us to build programs that can interact with messy data, with noise in the world. And it introduces a level of robustness that no other class of tools gives us. Of course, all of you are already using machine learning based applications, either knowingly, well, I'm hoping knowingly, and we'll talk about that as we go along. Machine learning is related to many, many different other fields. These are all active research areas. Machine learning is a powerful driver for modern artificial intelligence. It's not the same as AI, it's a tool. The goal of AI is to build computers that are as intelligent as humans, and machine learning is a critical component of modern AI. Machine learning draws from theoretical computer science and mathematics. We'll be looking at how to formalize the concept of learning mathematically, and it draws quite heavily from statistics and such related areas, and also from core ideas from formal computer science. It uses linear algebra, probability and statistics, the theory of computation, and modern machine learning is heavily built upon mathematical optimization. All of these things converge into the tools that we will be looking at. There's also connections, a little bit philosophical, to psychology, to neuroscience, to linguistics, and such areas where, as humans, we have shown the ability to learn, right? So the connection to these sorts of areas allows us to get inspiration for building programs that can mimic that. And of course, there are many applications. I talked about AI as an application. You can use machine learning in medicine, in engineering, in psychology, in marketing, in all those other areas that I listed. And it so happens that every year when I teach this class, the composition of the class tends to reflect the diversity of fields that machine learning draws from. I've had students here from all of these areas, gone on to do projects and PhDs in these areas using machine learning. Any questions? Questions about any of these things? Anything that you've seen so far? One advice that I was given when I was a grad student was, when I pause for questions, I wait for 30 seconds. And someone will feel uncomfortable enough to break the silence. Yes.
When we had a definition for machine learning, you said that there's a respect to some tasks.
Yes.
Why is it that we continue to consider machine learning respect to only certain tasks when a computer can be given like infinite tasks? It doesn't have a physical limit like the human brain.
Sure. The reason is so that you can actually empirically understand whether there are improvements. Only in theory, you would want this to work on an infinite number of tasks, but you cannot do measurements on infinite number of things. So you need upfront. So this is more about well-formed experiment design. So in order to understand, in order to show that the program is learning, you need to commit to the task and the performance measure upfront. Otherwise, your experiment might not be feasible. Does that?
Yeah.
Other questions? If not, I'm going to get into what we will see in the semester. So let's look at what we'll actually encounter in this semester. Throughout the semester, I will keep coming back to this question, what is learning? We will try to approach this question using different formal lenses. And each way of answering this question, it turns out, gives rise to different families of learning algorithms. Each way of answering this question will lead to new techniques for inventing learning algorithms. Along the way, we'll see different kinds of models, different learning protocols, different learning algorithms. We'll look at computational learning theory, and we will sort of touch upon, maybe skirt around the question of how to best represent data. Let's kind of dive into each of these points one at a time. We'll see different kinds of models. And I put the word models in quotes because that word has too many meanings. What I mean here concretely is we'll look at different kinds of functions that the learner learns. In the badges game, the function was, if the name has some property, the labels are plus. If it does not have the property, the labels are minus. That's a particular kind of a function. There are other kinds of functions. There are something, the first thing we'll encounter is something called a decision tree. We'll look at linear classifiers. How many people have seen linear classifiers before? Many of you. We'll look at linear regressors. If you've not seen it, don't worry. You'll see so much of it that you'll get tired of it. We'll look at non-linear classifiers, which is honestly not a great name because linear and non-linear, that's the entire universe. Specifically, we'll be looking at neural networks, and if time permits, we'll look at something called kernels. And another kind of a function that we will look at is this something called an ensemble, which is really a committee of different functions that together decide on what the answer should be, which itself becomes a bigger composite function. In parallel, we'll also be looking at, well, we'll not be looking at it, but in parallel, there also exist different learning protocols. There's something called supervised learning. In supervised learning, there's a teacher who assigns labels to a set of examples and gives these examples to the learner. Like the badges thing. That's what I did, right? I gave a bunch of names with labels next to them and gave them to you. And the learner's job is to use this labeled data set and try to discover what the hidden function was that the teacher used. In this case, the goal is for you to discover what the function was what the function that I used. And supervised learning is ubiquitous. Supervised learning is one way or another, most of the modern successes in machine learning, not all, but many, end up being instances of supervised learning. There's also something called unsupervised learning. There's no teacher here. There's just a pile of data, and the learner gets the data and is told, go figure. Here's some data, discover some patterns in the data. It's very intimately connected to ideas like clustering and data mining. Between these two things, there's something called unsupervised learning. The learner has access to a small number of examples with labels. And there's this big bucket of examples that have no labels. So in the badge example, imagine that you have those 6 names with labels, and you have 6 million names that have no labels. And can you somehow discover regularities in these 6 million names and combine it with the fact that there are 6 names with labels to somehow better discover the function that I have? Yes.
What makes semi-supervised learning different from supervised learning? Because as far as I can see, couldn't you interpret a semi-supervised learning problem as you have the labeled data and then the unlabeled data would just be the new examples provided?
In this case, the new examples provided always are going to show up eventually. You have the label. Let me give you an example. And this is also a kind of example that I will keep giving throughout the semester, so might as well introduce it. Imagine that you have pluses and minuses on the plane. So I have two pluses here and maybe two minuses here. And I tell you that I need to draw a line that separates the pluses and the minuses. And maybe you'll come up with something like this, right? Okay, but in addition to this, I'm going to give you some unlabeled examples. So there's a point here. There's a point here. These are all the points that exist in the in this space. And now I ask you, let me remove. You know what? Let me redo this. There are these points and then those points. And now I ask you, can you come up with a better line? And the original one was this thing here, which still separates the pluses and the minuses. But can the points that do not have any labels tell you something about the orientation of this line? Maybe you want to edit it. And the intuition could be, you want your line to not be too close to any of the, let's say you have unlabeled points here also. You don't want it to be too close to any of the points. You want enough separation, and maybe you want to draw a line that looks like this. So it helps you adjust your predictor without actually having access to labeled data by just knowing the distribution of the data. That's the hope. If this is too much detail, don't worry. We'll get into not exactly semi-supervised learning, but this style of thinking quite often as we go along. And then there's active learning. Active learning is really cool. In active learning, you have a teacher and a student who can actually interact with each other. It turns out that when students ask questions, they learn faster. Ask me questions. The learner asks questions to the teacher, and based on the answer to the question, the learner updates its internal hypothesis. And the way that works is that the clever bit here is asking the right question. If you ask the right set of questions, maybe with only a few limited set of questions, you can actually get to the hidden function much quicker. And active learning is a technique that's used for understanding, for reducing the cost of labeling data. Imagine that I want to build a program that can look at a chest X-ray and detect whether there are certain kinds of problems in that X-ray. The ground truth, the labeled data for that, if I had to operate in the supervised setting, I would first need to collect a whole bunch of chest X-rays and have a whole bunch of radiologists look at each one of them and tell me whether there's something wrong with it. Turns out radiologists are not cheap. Turns out that if I have to build a large collection of examples, I have to pay a lot of money. Instead, if I can do something like active learning, where I have a program where the learner says, I'm good with these kinds of chest X-rays, but there's something here that I'm confused about. Can you tell me what's going on here? And it gets that one piece of information and updates itself. With a very small number of questions, it can hopefully learn the concept. In this case, how to detect whether there's something wrong with X-ray. Another protocol for learning is called reinforcement learning. In reinforcement learning, there is really not a clear separation between the learner and the teacher and nature. The learner engages with the environment. It does things, it performs actions, and based on how well the action, based on the effects of the action, the learner gets a reward. And the goal of learning is to maximize reward over the lifetime. For example, imagine that I want a bot that knows how to play chess. And I'm too lazy to actually implement one of the standard chess algorithms. So I will have the bot play chess with another copy of itself. And every time it wins a game, the bot gets a point and it updates itself so that it does more things like that. If it loses a game, you don't know where the mistake was, but at some point it made a bad move and it down weights what the set of decisions that it did. And by doing this enough number of times, it can hopefully learn to play chess well, or at least play chess. Another example is, imagine that I have a self-driving car. Maybe that can be a very dark example. Let's say I have a self-driving car and it has to learn to stay in the lane. And every time it goes out of lane, nature somehow gives it a reward. I can think of ways in which you can reward a car not to go out of the lane with other cars in the side, but you can imagine. And every time it does that, it improves itself, and over time, hopefully, it gets better. Reinforcement learning and active learning are pretty hard to implement and conduct experiments with, because the sequence of steps that the learner takes changes the sequence of experience, the sequence of data points that it encounters. As a result, one run of a program might be different from another run. So the bottom two things tend to be difficult to do experiments with, but they also can be very rewarding. How many people have seen any of these things, in particular supervised learning, before? Several of you. How many people have used supervised learning? A few more. We'll be looking primarily at supervised learning in the semester, because the language that supervised learning, the terminology, the concepts that we'll encounter in supervised learning, it turns out will help us go to these other protocols. If you're interested, at the end of the semester, I will point you to other classes where you can learn about these other things also. Going back to what we'll see in the semester, we'll be looking at different learning algorithms. But in particular, I'm not just going to give you a bunch of algorithms and say, here they are. There are a few different kinds of learning algorithms out there, which relate to how the learner accesses data. And both of these are actually in the supervised setting. There's one class of learning algorithms that are called online algorithms, where the learner encounters one example at a time. And based on that one example, it can make a prediction, and then it gets feedback on whether it made a mistake or not. And based on that, it seems close enough to reinforcement learning, except it's much simpler than that. There's another way of thinking about learning, which is called batch algorithms, where the learner is given the entire collection of examples, and it has to do whatever it wants with it to discover the underlying rule. There are many different algorithms under each of these protocols. In this class, we'll be looking at an online algorithm called perceptron, which is perhaps the oldest neural network, one of the oldest neural network algorithms that are out there. We'll also look at a bunch of batch algorithms. If time permits, we'll do naive Bayes. We'll look at support vector machines. We'll look at logistic regression, neural networks, decision trees and nearest neighbors, and something called boosting, which is really a way of constructing a committee of models that agree with that create a consensus decision. All of these, there's a common theme here across all of these, where they're all given a set of examples, and the learner cannot go out and say, I need more examples. You have that batch, you just have to work with that. If time permits, we'll also look at one or two unsupervised or semi-supervised algorithms, in particular this idea called expectation maximization, and a special case of that, which is called the k-means clustering algorithm. I say that at the beginning of every semester. If time permits, we'll look at this. And the last time I taught expectation maximization was in 2015. Because I don't know why time never seems to permit. But we'll see. Some of you may have encountered some of these algorithms in the past, either looking into them in some detail or maybe using them as black boxes. How many people have used any of these things as black boxes? Some subset of you. Okay. The cool thing is in this semester, you'll be implementing most of these things from scratch. So hopefully you'll know how these things work on the inside. One of the big open questions in machine learning is, how do you best represent data? What's the right set of features that we need to extract from data so that your learning algorithm can discover the right concept? Let me give you an example. Take the badges example that we looked at, the badges game. I've already forgotten what, okay, you had a suggestion that the length of the first name and the last name are the same. How do you know that you need to look at the length? Maybe it's the font that was used that matters. Or maybe it was the color of the text. Somehow there's like a subtle difference in the shade. How do you know that you have to look at the length? How do you know that you have to look at these other attributes of the data? Which attributes of data are relevant? I told you that the name, the thing only depends on the name. But if I did not tell you that, how would you know that you don't need to look at the fact that that person was born on a certain day of the year? Everyone has a birthday, and maybe that's what decides whether they got a plus or a minus. If their birth, the date was even, then it's a plus. If it's odd, then it's a minus. How do you know which aspects of data are relevant for this particular classification or regression task? And how do you know that to avoid irrelevant features? Turns out this is extremely difficult to answer. Some of the easy cases are extremely easy, like in the badges game. You know very well that I'm not going to ask you to look at the birthday, because even though everyone has a birthday, maybe you don't know what it is. So I'm not going. It's almost like I'm not being adversarial here. But in some cases, you don't necessarily know what the right features are. A cool example that I heard of was around early 2000s. There was a hedge fund that tried to invest in coffee stock, I think in Starbucks, or some coffee stock. And what they did was they tried to get an edge over their competition. So they ended up buying the weather reports in Ethiopia and using the weather data to decide whether they should buy stock or sell stock. It turns out that at this point, I don't know exactly how coffee grows, so let me make it up. If it rains in a certain region of Ethiopia, the coffee production tends to be a little bit more, and it's a big supplier to this company that uses stock, buys coffee from that part of the world. And if the coffee production goes up, they're going to have a higher profit. If the coffee production goes down, they're going to lose money. And so if it rains there, Starbucks is going to lose money. This is a complicated feature. It required a lot of insight. It turns out, again, this is anecdotal information that I heard from the person who ran the hedge fund. Turns out they made a lot of money in 3 months, and then somehow mysteriously all the other companies figured out that they're using this, and the market advantage went away. So the point is, features can be extremely difficult. Another example, if I give you, do you remember the dog data that I showed you? If I ask you to write a program that detects what a dog is, using only the pixels, which of those pixels are dog pixels? How do you know what colors what the RGB values should be for an image to be classified as a dog or not? The right features, the right representation of data is such an important problem that perhaps the biggest jump in performance of machine learning systems came about around in the last decade, because the question of identifying the right features was itself made into a machine learning problem. That's what neural networks do. They discover features from data. And there are other aspects to representations like dimensionality reduction. I say if time permits, let me tell you right now, we'll never get there. The common theme across a lot of these things is the theory of machine learning. The learning is a phenomenon that we humans almost take for granted. It's a psychological, it's a cognitive function that we have. How do we convert that into mathematics? How do we convert that into a formal theory? There are at least 3 big formal analyses of machine learning. They don't disagree with each other. They kind of all feed into each other. One of them is one theoretical formalization of machine learning involves something called online learning, where the learner sees examples on a screen, and the hope is it stops making mistakes as it goes along. And the theoretical formalization there is what properties can we expect from a learner such that it satisfies that condition. And you can kind of prove that certain kinds of learning algorithms on certain kinds of data will never make mistakes after making a certain number of mistakes, or will minimize regret. Regret is this idea of changing decisions after having seen more data. Another analysis for machine learning is this fantastically named, probably approximately correct learning. And the idea here in the form is to try to formalize the following notion. After seeing a collection of examples, the learner will produce an approximately correct rule concept. But it's not guaranteed to do it all the time. It'll probably do it. With high probability, you'll discover a function that is correct, but maybe you just got unlucky. So the pack learning tries to formalize this notion of how many examples do you need to see so that you don't get unlucky too much. Another way of formalizing learning builds upon Bayesian theory. Bayesian learning is essentially asking what's the probability distribution over all possible functions. Imagine you have mathematical functions, which are really what the rules are. Can we come up with a way to characterize the probability distribution over all possible functions so that the true function that nature used or the teacher used has the highest probability or has high probability? What can we do to make this, to provide such a guarantee? It turns out each of these theoretical formalizations of machine learning lend themselves to new kinds of learning algorithms. From the online learning perspective, we get the perceptron algorithm, which is, like I said, an old machine learning algorithm. From the pack perspective, not exactly that, but kind of as an offshoot of that, we get something called the support vector machine. From Bayesian learning, we get something called logistic regression. And as we go along, we'll see that these 3 algorithms are very, very, very similar to each other. They behave very, very similarly. And that will be like a convergence that we'll get to maybe in the last month of the semester. This course is about the underlying concepts and the key algorithmic ideas that pervade machine learning. At the end of the semester, hopefully you will know how to think about machine learning, and if necessary, how to make the right choices for using machine learning. And if you're excited enough by what you see, maybe you want to do research in machine learning and invent new algorithms or invent new ideas, or maybe you want to use this for some sort of, you want to apply this to other things. What this course is definitely not about is a particular tool for machine learning, or a particular software framework, or any one learning paradigm, even though there are certain learning paradigms that are far more popular today. Because I'm hoping to equip you with the mental models about how to think about machine learning. Any questions? What time does the class end? Okay. I don't know why. In the first lecture of every semester, I always get confused about that, and I end up going past or end too early. So this is what we looked at so far is what you will learn. What you learn is you learn a broad theoretical and practical understanding of machine learning paradigms and machine learning algorithms. Through homeworks, you will get the ability to implement learning algorithms. And also through homework, you will get an appreciation for the people who implemented learning algorithms before you. the engineering part of it. And through homework and through discussions and through a project, you will learn where and how you can apply machine learning and make the appropriate decisions about which algorithms you can use and what kinds of data and what kind of supervision you can use and all the various knobs that every algorithm comes with. And this is something that is not something that's taught explicitly in a lecture. It comes by doing the homework and such things. That's what you will learn. The next question is, how will you learn all this? And that's the segue into the more boring logistical aspects of the class. The first lecture tends to be mostly logistics. I don't like starting off with logistics about Piazza and such things, so I wanted to introduce something technical today. But that's the technical part for today. Now the thing is, how are you going to learn all these things? So there's a class website. There's a URL there. You don't need to write it down. It's available on Canvas. All the lectures will be posted on the class website, the PDFs and such things. And we'll be using Piazza for discussion. You should be able to access it via Canvas. If you haven't been to Canvas already, I encourage you to check it out. You should all have access to Canvas by now. I believe you should also, I am told by a reliable source, that you all know how to access Piazza through Canvas. I'm not going to try to understand how. For me, it shows up as a link on the left-hand side of my Canvas. This class is, of course, in person, but if you need it for any reasons, the class is also being live streamed on Zoom. There's a link to that on Canvas. And because it's live streamed on Zoom, I figured it's also easy to record the class. So I do record the video. None of you show up in it, so don't worry. I don't show up either, I think. And I will be posting these lectures on YouTube after the lectures are done. If not on YouTube, I'll be posting a link to these lectures on Canvas. Watch Canvas for announcements and submissions and grades. Anything that you will be submitting to us, the information for that will be through Canvas. Any questions? The next logistical item is about people and meetings. The class is here now. I don't need to tell you that. I have office hours every Thursday at 10 a.m. And we have two teaching assistants. Oliver's here and Purvit's there. Maybe you can stand up and say hi, just wave. Both of them have taken machine learning this class last year, right? And did so well that I wanted them to come back. They have their own office hours and the times are still under discussion. So there'll be an announcement on Canvas about this sometime soon. Also the locations. I strongly encourage you to participate in class. And I say that not just because that's what's supposed to be said at the beginning of every class. It's well understood that active learning is successful. It's well understood that engaging with technical material allows you to understand it better. And if that's not enough motivation, think about another point. If you have a question, probably 10 others have the same question. And by asking a question, you're doing your friends a favor. Participation always aids understanding, and some of the material that we'll encounter can be pretty complex. So please do participate. There are many different ways in which you can engage with the class. In person, of course, you can ask questions. Raise your hand and ask a question. And if you feel like it, you can also answer your peers' questions. So that tends to lead to interesting directions. If you're on Zoom, You can ask your question via chat. I have the chat window open here. The TAs are also monitoring those. And if you feel brave enough, you can also unmute yourself on Zoom. I don't know why nobody does it. We are open to suggestions for improving engagement. The other way in which you can engage with us is through Piazza, with each other also, and Canvas. I prefer that you don't use the Canvas discussion boards, because then we'd have two things to monitor. Let's keep all discussion on Piazza. How do you communicate with us? You can send us messages through Piazza. Canvas also has its own email. I prefer Canvas emails to emails in my inbox, because at least then I will know to keep an eye on it. Please contact us through Canvas, through Piazza, or messages. If it is not private, I encourage you to post it on Piazza. If there's anything private, anything sensitive that you want me to look at, do send me an email. Don't feel shy about that. And just be aware that my inbox is heavily burdened these days, so I might be a little slow in responding. We'll be using Canvas for any announcements. Any announcements related to the class, watch out for Canvas. I think you probably already got an announcement today. So if you got it, then the system works. One person nodded your head, so I'm assuming he represents everyone. How will you? There are a lot of details on the class website. I encourage you to go over those details. In this class, the material that we will look at will build upon the basics of probability and statistics, some amount of linear algebra, enough computer science skills so that if I show you an algorithm in class, you should be able to go and implement it in your favorite language called Python. We'll talk about languages later. There's no required textbook. The class is self-contained. That doesn't mean that you can't refer to textbooks. For every lecture, I have posted reference material that you can follow up on. And if you find other useful references and resources and you want to share them with the class, feel free to do so. The lectures will be posted on the class website as well. And if you are unsure about any of the prerequisites, there's a growing collection of resources about things like linear algebra, probability, propositional logic for certain parts where we need that. These things are on the class website. And there's an FAQ section that I think also points to these things. The other part that students are typically interested in around this time is how do you get points? How do you get grades? You will have 6 to 7 assignments through the semester. And they will account for a bulk of your grades. There's a midterm exam, there's going to be a final exam, and there will be a project. And all of these will aggregate together in these ratios. Depending on how things go, I might actually slightly tweak them, most likely not, but I'll let you know if I do. Yes.
When I looked at the breakdown like this on Canvas, the percentages are different on that compared to what I saw on the syllabus.
The Canvas, there is no breakdown. There's nothing on Canvas yet.
I thought I saw something.
So the Canvas, I tend to add assignments one at a time.
Okay.
So right now there's only one assignment, turns out.
Okay.
And so it'll seem like 100% of your grade depends on this one thing that you're going to do this week. It's not. Don't worry about that. Because this class has both grad students and undergrads in the DS program, grad students will have to do extra work and work harder for those points, and will be curved separately from undergrads. Historically, I have found that undergrads tend to do better than grad students in this class. I do not know why. But don't, so if you're an undergrad, don't feel intimidated. If you're a grad student, that's a challenge for you. Like I said, there'll be 6 or 7 homeworks, roughly one homework every 2 weeks. And in the homework, grad students may have extra questions. Many homeworks will involve a programming component. And we strongly prefer Python for the simple reason that a lot of professional machine learning development in the industry uses Python, and I figured might as well get you started on that early. And also, I know that several of you are comfortable with the language already. We'll be specifying a list of libraries that you are allowed to use. In particular, for example, for any of your homework and your project, you should not be using any machine learning library because then there's no point. If you absolutely hate Python, and I don't blame you, if you absolutely hate Python and refuse to work with it, come talk to me, and I'll try to convince you the wisdom of using this language. And if you are completely uncomfortable with Python and use, I don't know, R or MATLAB or something, talk to me, we'll see if we can figure it out. The biggest sticking point with other languages is we may not be able to give you, read your code in that language if you are not comfortable with that language. And so you may not get partial credit. So I strongly prefer Python if you are going to do this. Of course, all homeworks have to be digital submissions. This is not for the programming component. Of course, the programming component is digital, but anything that's written or anything that's theory, please don't write it and slip it under my door. My handwriting is terrible and I expect nothing less from you. So please submit your homework digitally. Every homework will contain instructions on how to submit. Yes.
Can it be handwritten but then scanned?
As I was saying what I said, I was thinking I'm leaving. There's a loophole here. I prefer not because these two guys will be grading your stuff, and you want to make it easy for them. I prefer not. So the late policy for the class is that for every assignment and also for the project milestones, if you submit on time, you get whatever points you get. If you then you get 24 hours extra. In the next 24 hours, if you submit any time in the next 24 hours after the deadline, you lose 10% of the points. So if you were originally going to score 90, you lose 10%, you lose 9 points, so you get 81. And after 24 hours, we'll not accept whatever you submit, unless the only exception I will make for that is if there is any health-related issues where you get me a letter from CDA, for example. So I'll come to that later. And then there's a project component in the class. The goal of the project is to show what you learned in the class. So you'll be using ideas from the lectures and homeworks on a data set that I will discuss. I will send you the data set. I'll talk about that in a later lecture, where you'll all be working on the same data set on a shared task and technically competing with each other on Kaggle. Have people seen Kaggle before? Some subset of you. It's this platform where you can upload your, you can train classifiers, you can train models, have the predictions, you upload your predictions, and it will automatically be graded for accuracy. And you'll all be put on a leaderboard. So you'll work on projects individually on a shared data set where you'll be implementing algorithms that you encounter in the class and throwing it at the data set to see what happens and where you stand on the leaderboard. There are several milestones for the project, and I'll talk about that in a minute. But importantly, where you stand on the leaderboard is not going to change what grade you get, unless it's at the very bottom where your program, it turns out, is actually not doing any machine learning, but tossing a coin and just predicting a label. So as long as you do the right things, make the right choices, and you'll be submitting reports on what you did, and your leaderboard position reflects those choices, because we'll be implementing many of those algorithms as well. Your leaderboard positions are kind of in the ballpark of where you ought to be according to those choices, then you'll get your points. Okay. There are many milestones for the project. There are 4 milestones for the project. There are details on the class website, but very briefly, at the very beginning, not too long from now, you'll be submitting for a very small number of points, information about your Kaggle account. That will allow me to connect your Kaggle account to for grading. If you miss that milestone, I cannot give you the rest of the grades. So it's a very important milestone. Another milestone involves you'll be implementing 1 hour, then you'll be implementing 2 more, and then at the end of the semester you'll do 3 more, so then you'll have 6 hours. There's going to be a detailed document that lists out all these things in a week or two, in a few weeks. Any questions about homeworks and projects?
Also, like, if I submit my assignment, will I get some remarks in few days, or at the end I will get just my marks?
You will get, it will not be a few days, let me tell you right now. It'll be, you will get detailed, you'll get some amount of detailed feedback. And of course, if you want to discuss that, you should come to office hours, and we are always very happy to give more feedback. Yes.
Will solutions to the homework assignments be released after they've all been graded so that we can
Yep.
compare?
Of course, yes. Other questions?
My background is purely MedDev, right?
Is what?
I mean, I've worked only on MedDev in the bachelor's and the master's, right?
Okay.
Even now, I have to learn Python, that is mandatory for me.
So you don't have to,
It's a-
so,
it's resources.
okay, let's talk about that. Let's just meet me after class. If you only use MATLAB, we'll have a chat.
Now I have to work on Python.
Let's talk. If you strongly feel like you don't know Python at all, we may make some exceptions, and my TA is giving me a dirty look. We may make some exceptions. So let's talk about class policies. The most important policy is that you need to look at the syllabus. There are many, many policies. So please take a look at the syllabus. I'll quickly summarize things. This class operates under the School of Computing policies, and if you've taken any CS class before, you've seen this content. In particular, the policy on collaboration and cheating. Collaboration is helpful. Talking to each other helps you learn better. But that doesn't mean you ask your friend to do your homework for you, because then you don't learn anything. So cheating will not be tolerated. Any submission that you have should be written by you, should be coded by you. The School of Computing has a policy on academic misconduct. Please take a look at that. Importantly, if you the first time if you're caught cheating, you get a 0 for whatever that submission is, and there will be a letter sent to the department. If that happens again, you'll be kicked out of the class. But the details aside, don't cheat. I mean, there's no point. There's no point because you don't learn anything. This means that if you refer to external sources or resources, please acknowledge them. And these external sources also include things like language model. Your submissions, the text that you write in your submissions, and the code that you write in your submissions should be your own. It should not be generated by someone or something else. And of course, nothing is a group submission. Everything, all of you work individually. Yes.
If there's, say, code that we write that utilizes a library, an external library, can we do that so long as we note that we have used it?
Yeah. I mean, of course, you're going to use some external libraries. I'm not going to ask you to implement a compiler from scratch. I'm not going to ask you to implement Python from scratch because it's also external. So yes, there will obviously be external libraries that you will use. In particular, I'm thinking pandas and numpy. So you will be using those things. If you need any kind of assistance to navigate the material, please contact us as soon as possible. For the large part, we will process these things via the CDA, Center for Disability and Access. If you need any accommodations, extra time and such things, whatever their recommendation is what I'll follow. There are additional policies on safety and such things on the class website. You can take a look at it. There is wellness and health and such things. And there are many things that can be stressful in life. I don't really want the class to be one of them. So if you need any sort of support or anything, feel free to use those resources, or I'm happy to chat. And I'm happy to chat. Any questions? One thing I realize is when I'm teaching a class of this size, you all know who I am. I don't know you. So there's a survey on Canvas. Feel free to fill out as much of it as you want, if you want to. And this is mostly for me to know who you are, what your interests are. And the goal is, I may be able to tailor the lectures to your interests. If you have certain specific interests, let's say that you are extremely passionate about knitting, and you participate in the Olympic knitting competition. Maybe I can come up with examples that involve machine learning and knitting. I don't know. So it helps me design lectures for you, but also it helps me understand who you are and what your motivations are. So this will be open for a week. Feel free to fill it out as much of it as you want, and there's no compulsion. Okay, any questions? That's pretty much all we have for today, except for one thing. There's a homework. I know. There's a homework 0 that's available on Canvas. Homework 0 is got nothing to do with machine learning. It's more about the prerequisite. It's mostly for you to refresh your memory about the prerequisite. Everything on homework 0 should be fairly easy. And if it's not, at least it forces you to kind of accumulate the material you need so that when we encounter something that's related to that, you know what to look at. So you get a week for this. This accounts for a tiny part of your final grade. And this is a Canvas quiz. You get 2 attempts at it. And the highest score is what remains. Okay, I will see you on Thursday. Please fill out the survey. And if you have any questions or anything you want to discuss, I'll hang around here for a bit.